All right, we're going to talk about the last topic in chapter 12. It's called angular momentum. And you remember, sorry, when we had momentum, we did it as lowercase p. Momentum is equal to mass times velocity. And it's a vector. It has a direction because velocity has a vector. So when you're moving in a straight line, you have this quantity called momentum, invented by Newton. You also have momentum if an object is spinning. So if we have a disk that's spinning around, it obeys the same properties in that when it has its momentum, it wants to continue with that same momentum. So if it's something that's spinning, it wants to stay spinning forever. And the only way to stop the spin is to apply a torque. Just like the only way to change something's linear momentum is to apply a force. To change an angular momentum, you have to apply a torque. Now that torque could be like friction with the air. But if you had some place where there wasn't any friction and something was spinning, it would spin essentially indefinitely as long as no other force acted on it. That is pretty much why the Earth spinning on its axis is spinning on its axis, and it's not slowing down. Well, that's not true. It's slowing down kind of, but it's slowing down mostly because the moon is stealing our angular momentum. But if it was by itself, just spinning around, there was no other forces acting on it, no torques, it would essentially spin around forever because there's no friction in space. All right, so angular momentum is just going to be, and this is a little tricky here because if you have a point source, so if we have like a point and it's rotating around an object, then this angular momentum, we call it L, is going to be its linear momentum times the radius vector. So if it has a radius vector, this is our rotation point in the center here, it's going around like this, so something orbiting, it's going to be mass times the velocity times the radius vector. Or technically, if not really times, this should be a cross product. So let me fix this. This is going to be the linear momentum times crossed with the radius vector. This is the cross product here. And if you remember, we already talked about cross product. Well, cross product means it's going to be the linear momentum times the radius times the sine of the angle in between them. But we can write this as mv, so this becomes mvr, sine of the angle between the velocity vector and the radius vector. So that's where I was going to right away, but we had to show you how you get here. Okay. Now in this case, the radius vector is this way, the velocity vector would be this way, and that, if that's a 90-degree angle, this becomes 1, and it's just mvr. So it depends on what that angle is. If something's in a nice, perfectly circular orbit, that becomes 90, and this is just mvr. Now what if you have a solid object like I had here, like a spinning disk? Well, a spinning disk is not a point source spinning around. You have to worry about the distribution of mass. So in that case, L becomes I omega, where I is your moment of inertia, the distribution of the mass about a rotation point, and omega is the angular velocity. So you're going to use combinations of these. If you have, this is for a point source, this is for an extended object. And we're going to do the same way we did with momentum in the past, is we're going to do this as conservation of momentum. Instead, though, this is going to be conservation of angular momentum. So when we have two things interacting that are rotating, we have to say that the angular momentum initial is equal to the angular momentum final. Okay. Now if it's the same thing, like it's two disks spinning, and like part of the disk changes, so the distribution of mass changes, then this is I initial, omega initial is equal to I final, omega final. This actually happened to the Earth because the Earth is a spinning sphere, and it has an I and its omega value. Well, when there was the earthquake, a very large earthquake, the Christmas earthquake many years ago now, it actually shifted the eye of the Earth slightly, but it changed the final omega, because from the initial, this was the angular momentum it started with, and then you change I, well, omega has to change to account for that. So as like the crustal plates shift in the Earth, you can change I, which changes it. Now it's really slight. It's a very, very tiny effect, but it does make a significant change, and it will rotate different. This is also the case for a skater spinning around. So an ice skater spinning with their arms out. Well, with their arms out, their eye is much bigger, and then they pull their arms in. They haven't added anything, so whatever their initial momentum is the same. They haven't pushed off, they're just spinning around. Okay. Once they pull their arms in, they change I. They make I smaller to keep the same value. Omega goes up, so they spin faster. So that is just a demonstration of conservation of angular momentum. Let's do a problem here. So this will help make more sense. In problem 78, we have a door. So this is our door right here, with hinges on this side of the door. And it is a 1 meter wide door, 1.0 meter wide door. And we're going to shoot the door. We're too lazy to close the door. We want to close the door, so it's going to spin like this. But we're going to do it by shooting a bullet into the door. The bullet has a speed of 400 meters per second, and it's a 10-gram bullet. Okay, and so what we want to do is figure out what the omega final is for the door after you shoot it. And we're going to shoot it out here at an exact 90-degree angle furthest from the hinge, so our radius vector is going to be the length of the door. So this is going to be initial, angular momentum initial is equal to angular momentum final. Well, the door is not moving to begin with, so it has no angular momentum. But the bullet has angular momentum. Okay, but it's a point source, so we have to use this value up here. So you're going to use one of these two. These are the formulas you need to know. So this is the point source. So we're going to say, oh, this is mv, that's the mass of the bullet, times the velocity of the bullet, times r, times the sine of the angle between them. Must be final, but the final is going to be I because it's an extended object rotating, times omega final. Now the bullet embeds itself into the door. Okay? So what we're going to say is the sine of this is 90, so that's just going to be 1. So this is going to be mass of the bullet times the velocity of the bullet times the radius is equal to I, but I has two parts. I for a rectangle spinning like this is 1/3 ma squared. If you look it up in the table, page 300. But a is just your radius, or the distance, the width of the building. So in our case, a is just going to be equal to 1. Okay? But you also have the mass of the bullet. It's very tiny, so it's really not going to make an effect, but it could in some cases. But we have to add in that to the door. So I is going to be equal to the door, 1/3 of the mass of the door, times its radius squared, or its width squared, plus the mass of the bullet, which is going to be mr squared, which that's the mass of the bullet, all times omega final. And if I solve that for omega final, I'm going to get the mass of the bullet times the velocity of the bullet times the radius over 1/2 the mass of the door times the radius squared plus the mass of the bullet, radius squared. All that should be equal to omega final. All right. So we can just plug in all the numbers. And we have that the mass of the bullet is 10 grams, so we got to convert this to kilograms. So this is 0.010 times the velocity is 400 meters per second. The radius is just 1. On the bottom here, we have 1/2 times the mass of the door. And the mass of the door is 10. Sorry, I forgot to put that down there, but it's a 10 kilogram door. Times the radius of the door, which is 1 squared, plus the mass of the bullet is 0.010 times 1 squared. But the 1 squared and the 1's all just kind of, 1 squared times 1 is just 1. And none of that changes. You plug all that in and you get omega final is 1.2 radians per second. So that's how you do them. You're going to do them as conservation of angular momentum. Try these problems here. I just did 78, do 79, 81, and 82.